In this video, I will go over sets and answer what are sets, when do we use sets, as well as how to use them, and some practice on set operations in C++. Sets are data structures or abstract data types, and they are used to store a collection of elements with a feature that is unique keys. So a set of integers has the property of unique keys, meaning that every integer inserted in a set has to be different. It is similar to maps, where we have key-value pairs, but we use sets when we only want to store the keys. And we have two types of sets, ordered sets and unordered sets. In C++, the set keyword is for ordered sets, and its underlying implementation is binary search trees. For unordered sets, they are implemented using hash tables. So sets are very similar to maps, but we use them when we only want to store keys. So let's see. In maps, we have collisions, which are caused by, in a case where you want to insert a key of the same that already exists in the map, but with a different value. In sets, however, we do not have collisions, because when you try to insert an element, let's say we have a set of integers 1, 3, 5, 7, and we try to insert 3 into this list. In sets, that does not work. This new number that just got inserted does not get inserted actually, and the size does not update, so it basically gets ignored. For this reason, we do not have collisions. But hashing works very similar to how the hashing function works in maps. First, the key is used inside the hashing function to produce a code, and then this code is used to store the key in sets, as well as to retrieve it. The key from the set. So let's say in this case, the first key is 1. This key is inserted into the hashing function and gives us like a hash code. This hash code is used to store the key in the set, and it allows for very efficient retrieval from the set, which is why in sets most of the operations are very efficient, including searching. So because sets are implemented using binary search trees, the time complexity for most of the operations are going to be log of n on average, which is why I prefer to use unordered sets, because they are implemented using hash tables, and actually the hashing function is used to map the keys to indices in an array. So the underlying implementation is an array with a hash table that uses this hashing functionality. The operations, as you can see, they're going to be big O of 1 on average, which is the most efficient. And next we're going to look at how to use the sets. So first step is to include the set template and the unordered set template based on which one you're going to use. And then you can use the keyword set or unordered underscore set. Make sure to indicate the type In this case, we have a set of type int with the name of O underscore set, standing for ordered set, and then we have an unordered set, which is called uset. We can insert into a set by using this insert function. So in an unordered set, when the elements get inserted, we are not guaranteed any specific order. But in an ordered set, the elements will be ordered by their value. We can remove elements using the raise function, find elements using this function, which returns either a pointer to the key or a pointer to the, so we have either a pointer to the key or end of set. We can access elements in a set by the square brackets, like indexing, and this is useful when you want to like update the value. So you can set this to 3 and the value should update. We can get the size using this function, whether it's empty or not, and a count. In most of the cases, the count is going to be 1 because of the unique key feature, but there's a case where we have a multi-set inside the set library, where multiple keys with the same value could be inserted, and they will be like treated as different keys. So using this count, it gives you back how many elements of this key exist. And this is like practice of how it would look like when you try to practice it. First you include the set and unordered set, and then here I'm initializing them, declaring the sets, and then initializing them with values. In the unordered set, those elements are not going to be in the same order as they're inserted, or depending on the value. But in an ordered set, it is going to be guaranteed that they're going to come in the order based on the values. So this is how you can, it's one way to iterate through a set. Basically for every I here, which is every element in the ordered set, we're just printing it. Same thing for the unordered set in this section. I recommend you run this code to see how the output looks like, so understand. And then here I'm using the size operation on both the set and unordered set, as well as the count operation. In this case, the count is 1 for both, but on this line and these two lines, we're asking for the count of 4, which does not exist, which just returns 0. Yeah, and then the find operation, it returns either a pointer to the value, so you can dereference it and it would give you the actual value 3, or it's going to be pointing to the O underscore set dot end. And as you can see here, if it's not equal to the set dot end, meaning that the element does exist in the set, we just print it and you're going to get 3 in this case. Else not found. Okay. Yeah, you can try this on 4, which is not found, and you'll get this message. Here I'm erasing 3 from the list, and then I'm trying to iterate through a different method. In this method, we're starting from the beginning of the set, which is a pointer actually to the first element. And then we keep iterating that pointer, dereferencing the element, and it basically prints out the element for you and traverses through the set. Lastly, I want to go over multi-sets really quickly, just show you how they perform. All the operations have the same time complexity of sets on average, so O of log of n, plus this additional feature that allows you to insert the same element twice and being treated as different keys.